Hello and welcome to day 2 with me, your naughty professor. Today we're going to be learning a little tiny bit about trigonometry. We're going to get really up close and personal, and I'm going to show you all the dirty little secrets. Since we're going to be so friendly by the end, I thought we could call it by its nickname, Trig. I'm going to explain 3 different ways of viewing sine and cosine. We'll mostly focus on those two, and then we can talk about their other friends, tangent, secant, cosecant, cotangent, some other time. But today I want to think a lot about sine and cosine, and I want to relate 3 different ways of thinking about them. A lot of students only understand them, if at all, in one of the 3 ways, either on right triangles, on the unit circle, or as curves. I want to relate all 3 of those things together for you so that it doesn't just seem like suddenly these functions are popping out of nowhere. We're dealing with nice, pretty parabolas, and all of a sudden here's sine again, and I thought we were done because we're not doing geometry anymore. So let's get started. I'm going to start with triangles, then we'll go to unit circles, and then I'll introduce the curves of sine and cosine functions. So let's get started with a triangle. This is a right triangle, and you can tell it's a right triangle because I'm going to draw a little box right there. That box means I've got a 90-degree angle. I've also got some other angles. They can't be 90 degrees because a triangle can only have 180 degrees in it, and this guy's hogging all the fun. We've already got 90 degrees. There's only 90 degrees to add up here and here. If this guy's 90 also, what we'd end up with is something like that, and these guys are never going to meet up. So, long explanation for why this special little angle that we're going to call theta, and you can call it anything you want, we call it theta by convention. When I say we do something by convention, I mean a bunch of old white guys decided that that's how we should do it, and we tend to listen to old white guys, so that's what we've been doing this whole time. There's no good reason for it, but generally, if we're picking some random angle out of nowhere, we don't know what it is, we're going to call it theta. You've probably seen the random angle called x, but I like to save x for algebra. Usually Greek letters are appropriate for angles. Here's theta, and we're going to identify everything else based on theta. Theta is the protagonist here. Theta is the important angle. This is really important because there are some other angles going on here. We've got a right angle, we've got whatever the hell's up here, but theta is our pride and joy. Theta is the important angle. The triangle isn't the important thing. Theta is what we're actually focused on. And we're going to name things based on how they relate to theta. Theta is across from this side. We could say it's opposite this side, and so we call this opposite. O for opposite. This side is next to theta, and so we call it adjacent. A for adjacent. And this side, well, it doesn't really matter how it pertains to theta because it's the hypotenuse of the triangle. This is the one that doesn't actually care that much about theta. This is the hypotenuse. H for hypotenuse. And we can define sine and cosine from here. That's really important. I'm not discovering sine and cosine. This is where we can actually say they come from. I can actually start with a triangle and then say, okay, and then the relationship between those sides, we're going to give it a name. And all of math just comes from giving shit names, okay? The number 5 just came from, oh, I have the same number of fingers here as I do here, and if I gather up a bunch of sheep, I could have one sheep for each finger, and I could have one rock for each finger, and they're all the same number. Let's give it a name. This is where everything comes from. It's just as I said, old white guy's making shit up. So, the name for this is the hypotenuse, adjacent, opposite. Hate inconsistency. I underlined one. I should underline all three. And then we're going to define the sine and cosine functions from there. Let's do it. We say the sine of theta is the length, the measure, the distance of the opposite side divided by the length of the hypotenuse. So we could write that as opposite over hypotenuse. And we can do the same thing with cosine. I'm going to define the cosine of theta to be the adjacent over the hypotenuse. So these functions are just coming from some ratios on the triangle. And the exciting thing here, the reason we can do this at all, is because those ratios are going to be consistent. If I make this triangle smaller, I'm making this side smaller by the same proportion that I'm making this side smaller, and that I'm making this side smaller. If I have a new HOA, these ratios are going to be the same. And that's why I'm not saying the sine of the triangle, the cosine of the triangle, I'm saying the sine and the cosine of this angle theta. Because any right triangle I draw from theta is going to have those same measures. Alright? So let's keep those things. Let's keep that idea of sine and cosine coming from a triangle, and I'm going to go into circles. You can probably remember what we were calling things. Hopefully. If you're a good student. So here's our givens. Here's what we're remembering. We're remembering that sine of theta is the opposite over the hypotenuse, and cosine of theta is the adjacent over the hypotenuse. So that's for any triangle, or I've got an angle theta in here and a right angle at the edge. You might see sine, cosine used for triangles that aren't right triangles, and we can talk about that later, but basically it boils down to find the right triangle within the other triangle, and we're just going to focus on the definition for now because I want you to see it in a unit circle. So let's draw a circle. Not a perfect circle, but we'll call it good. This is called a unit circle because we're going to give it a radius of 1. You know, a unit. And we're going to go ahead and center it at the origin. Remember last time, we just called this our y-axis and it's our x-axis by convention. Then, somewhere on this circle, we're going to find a point. Let's start by making it a boring point and stick in what we call the first quadrant, where x and y are both positive right here. So here's our point. And that has an x value and a y value. It also has a triangle that goes with it. Would you look at that? It's just like the triangle we saw before. Since I've gone right down to this point, its x value, since I've gone right down to the x-axis without crossing go, I've just gone directly down in a vertical line to a horizontal line. That's a right angle. Alright, so this triangle might be flipped from what we're used to seeing, but hopefully we're clever enough to see beyond that ruse. Right here is an angle. Not just some random angle, let's call it theta, alright? I'm being sneaky here maybe, but I think you can probably see beyond my sneakiness to know that we're going to use this theta the same way we used the last one. Here's the exciting part. Before we had a hypotenuse. Okay, we still have a hypotenuse, but it's our very favorite hypotenuse 1. Can't do better than that. This line is adjacent to theta. This line is opposite theta. So, the sine of theta would be the opposite over 1. The cosine of theta would be the adjacent over 1. We're just replacing h with 1, okay? There's no rocket science going on here. Forgive me if I'm being a little slow. Alright, no magic. When we divide by 1, what happens? Nothing! I divide by 1, I just get the opposite out. Alright, this is where I wish that opposite didn't start with the letter O because it looks just like a 0, and I'm sorry, I'm not saying the sine's equal to 0. This is I can afford to write that in a new line. Sine of theta is opposite. Cosine of theta is adjacent. Like I said, I wish I didn't have an O here, so let's get rid of it. Let's give it a new name. And this new name, I'm going to choose kind of cleverly. In fact, I'm not going to choose it at all. I'm going to notice that we've already named this. If this point is x comma y, as it often is, this value here, I don't have to call it O, I can call it y. That's how high up that point is. This value here, I don't have to call it A, I can call it x. That's how far out I've gone to get to this point. So in fact, sine of theta equals y, and cosine of theta equals x. So this point right here has coordinates sine, comma, cosine. We didn't have to define it this time. This time we really did find it. This time we dug around, we saw a triangle. It's just like the triangle we saw before, and we used our definitions of sine and cosine in order to understand what was going on. And so any point here is going to be written as a right triangle. It's going to be drawn as a right triangle. It's going to be written as sine of a thing, comma, cosine of a thing, and that thing is going to be this point right here. You might ask, what if we go beyond that angle? There's a whole circle here to deal with, and if I'm going to go down here, if I'm going to bend over backwards and find a point over here, I'm going to have to draw sort of a backwards triangle. If I find a point there, I'm going to end up with sort of a negative x value, positive y, and that's exactly what's going to happen. Cosine, the x value is going to end up being negative. Sine will still be positive. Down here, they're both going to be negative because I'm going to the left and down. Over here, cosine is positive and sine is negative because I'm going to the right and down. But again, we can talk more in depth about that next time, but I really wanted to get this idea that the trig on a unit circle and the trig on a right triangle are the same trig. It's not two different concepts that just pop out of nowhere and seem to relate somewhere. There's no magic here. I mean, all math is magic, but it's nothing shocking. Last thing, I said we'd talk about the curves. I know you want to talk about curves. Let's do it. I'm going to draw you the sine function. This is my x-axis. But remember, the x is just sort of code for input. I'm going to actually call it my theta axis. And I don't really want to get confused by calling this x and y when we just saw x and y in a unit circle. So instead of calling this y, I'm just going to go ahead and label it sine of theta. So this axis gives me sine of theta, this axis gives me theta. Now, you're definitely going to see these labeled x and y. In fact, usually that's what we're going to label them. But it doesn't matter, it's the same picture, okay? Don't let anyone fool you. You're smart, you understand, we can just change the names and it's the same thing. On this theta axis, you're going to usually see these in radians. I'm going to write them in degrees. Forgive me. I can talk about how the radians relate in another video. So, a whole circle, that's 180 degrees, or that's 360 degrees. If I want to go all the way around the unit circle, that as well. Here we've got 180 degrees. Halfway, here we've got 90 degrees. And so this is where the exciting stuff is happening. This is our original triangle, just from 0 to almost 90 degrees. Remember that angle for the triangle, that angle theta couldn't actually get to 90 degrees because then stuff got funky. But on a unit circle, this triangle can get taller and skinnier until it's basically just a line. And that's what we mean when we go up to 90 degrees. So I'm going to focus on this little tiny chunk. I drew this big picture, but this is where the action is happening. I'm looking at this angle. So here's a triangle. I'm drawing sine, so I'm talking about the height. Oh, no, that's backwards. So I'm looking at this value right here. All right, if theta is 0, I've got a flat triangle. Not really much of a triangle. The height is 0. So if this angle is 0, if I'm drawing a line at an angle of 0 to that x-axis, I've got 0. If this angle is 90 degrees, if I'm drawing a line at 90 degrees to the x-axis, then the height is 1. In between, it's going to vary. There are 3 points that your teachers tend to want you to memorize. I don't know why we picked these 3, but they're nice. They give us really cute triangles, and we can talk about that again, like I keep saying, in another video, but 30, 45, and 60 degrees in this arc we tend to really focus on, and I'll just give you the values here, but all of those are just coming from a height. So if I have a 30-degree angle right here, it's going to end up being half. So 30, let's see, that's 1/3 of 90. It's going to give me a half. If I have a 60-degree angle, like this, it's going to give me √3/2. Okay, it's not great, but that's like a lot closer up here. If I have a 45-degree angle, that's halfway. It's going to give me a triangle with both base and height, √2/2. And that's going to be around here. That should be a bit higher. Actually, this should be a little bit lower is the problem. And then as this triangle sort of loops around the circle, the height gets bigger, 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 smaller, 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 negative, 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 more negative, less negative. These points are just going to repeat themselves. And that's why all the exciting stuff happens here. This gives me a full picture of the sine curve. But that's not what we usually see. We usually see that. We call this one period of the curve. We call it one revolution of the unit circle, and this is just a representation of what the sine curve is going to do everywhere. It's just going to keep going around and around and around on the circle, so it's just going to keep going up and down, up, down, up, down. You know the pattern. And we're going to see a sine curve and a cosine curve looking like functions when really it's just values coming from the unit circle. And we see things on the unit circle looking like they popped out of magic when really it's just coming from these triangles. So that's the big idea that I wanted to get across in this video. I wanted to convey the 3 different ways of looking at trig functions are really the exact same thing. All right? There's a whole lot that can be done in trig, and I know that there's a lot of curiosity, a lot of maybe confusion that comes from trig functions, and so that's why I'll strongly encourage you to let me know what you want to see. Is there something else having to do with trig, having to do with functions, having to do with triangles that's really getting at you and you'd really like me to explore it for you? Throw me a comment, a message, an email. I am naughtymathprofessor@gmail.com, and I will, if you're really lucky and really good, address that in a future video. Have a great time, and I will see you later.